Hello. Today, we will be discussing numbers. Now, you might think you understand numbers. Spoiler alert, you don't. If you're watching this video, you most likely don't understand the intricacies of numbers and the complexities of numbers. Although numbers can seem simple on the outside, there's a lot more to them than just simply 1 plus 1 equals 2. The numbers you're used to are integers. Those are numbers like 1 and 2 and 3 and 77 and 516 or negative 2004 or negative 5 and 0. 0 isn't negative or positive, so it gets its own category. Now, integers are part of rational numbers because they're part of fractions, which is the definition of rational numbers. Now, you might be wondering, okay, well, why are integers part of fractions? What is this? Well, it's really simple. 5 divided by 1 is equal to 5. Therefore, all integers are also fractions because you can put any of those numbers with a divided by 1 and bang, they're fractions. Even 0. You cannot divide a number by 0, but you can divide 0 by other numbers. It just stays as 0. Now, you might be thinking, well, okay, fractions are part of rational numbers, then where do decimals go? Fractions are decimals, just a different way of representing them. Just like with fractions, any of your good old integers are also decimals. 1 is also 1.0, and 2 is also 2.0, and so on. Similarly, fractions can also be written as decimals. This is pretty easy to do. If you have 3 divided by 4, all you need to do is divide 3 by 4, and bang, it is a decimal. 0.75 to be exact. Now, although me saying fractions are decimals is correct, decimals are fractions is incorrect. Because fractions, despite all being decimals, only represent a certain part of decimals. They represent finite decimals and infinite recursive decimals. So, what are the differences between finite decimals and infinite recursive decimals? Well, one difference is easy to spot. One of them is infinite, the other one is not. Now, finite decimals are everywhere. That's like a price at a store, $49.99. The 0.99, that's a finite decimal. It doesn't go over to infinity. It's just 49.99. Or, like I said earlier, 3 divided by 4 equals 0.75. That's a finite decimal. There's a set number of terms after the dot. An example of an infinite recursive decimal that you might encounter often is 1 divided by 3, a third. Because if you divide 1 by 3, you'll get 0.333333333 to infinity. Now, this is infinite because the number of 3's in the chain is infinite. However, it's also recursive because the only number that's going to appear there is 3. It's not going to go 0.333373333333333. It's always going to say 3's. But infinite recursive decimals aren't just a repetition of the same number. It can be a repetition of a set of numbers. For example, 1 divided by 7 is equal to 0.142857 to infinity. It's not the same number repeating over and over again, but it is the same set of numbers repeating over and over again, which makes it an infinite recursive decimal. Now, earlier I talked about converting a fraction into decimals. I can also convert a decimal into fractions. For example, the decimal number of 0.5. I can convert that into fraction because it's 5 divided by 10 equals 5 divided by 10. 5 divided by 10 is equal to 0.5. So 0.5 is equal to 5 divided by 10. Now, what do 5 and 10 have in common? A factor of 5. You can factor both 5 and 10 with 5, which turns into 1 divided by 2 if you divide both 5 and 10 by 5. Now, this can also go for quite a few other decimals, such as 0.25. You can put that as 25 over 100. 25 over 100, the common factor of both is 25. If you divide both by 25, you will get 1 divided by 4. And that's how you convert a finite decimal into a fraction. Infinite recursive decimals are still fractions, but the way you convert them back into fractions is a lot more complicated than with finite decimals. You're going to have to put into play high school math. To be more exact, geometric series and calculating the sum of geometric series. For this example, I'm going to use 1 divided by 3. Now, as I said earlier, 3 divided by 10 is equal to 0.3. Because 3 is like 5. They're both integers that are single digits, so if you divide it by 10, it's 0. That number. 0.3 is 3 divided by 10. Now, 3 divided by, say, 100, that would be 0.03. And then 3 divided by 1,000, that would be 0.003. Now, what would happen if you added those numbers together? You would get 0.333. And the beginning of 1 divided by 3's infinite series of numbers is 0.333. So theoretically, you could just 1 divided by 3 as an infinite series of 3 divided by 10 plus 3 divided by 100 plus 3 divided by 1,000, and so on and so forth. Now, you could simplify this even further by factoring 3 divided by 10 out of the series, making it 3 divided by 10 multiplied by 1 plus 1 divided by 10 plus 1 divided by 10 to the power of 2, and so on and so forth. And this is how you would feasibly represent 0.33333 as a fraction with a geometric series with common ratio of 1 divided by 10 and first term of 1, as you can see here. However, you might be telling yourself, well, I know that 1 divided by 3 is 0.33333. This complicated geometric series does not look like 1 divided by 3 to me. Well, it doesn't look like that to me either. And if it does look like that to you, you need glasses. Now, to put this as 1 divided by 3, you need to calculate the sum of this geometric series. Which, as you can see, is equal to 1 divided by 3. Now, in the interest of time, I won't go over how this works for more complicated infinite recursive decimals like 0.142857 and those types of numbers. Instead, I'll show you how to calculate those on screen now. So if you want to pause and screenshot to check it out later, go ahead. Now, once again, you've probably noticed, if you're paying attention, that I left something out. Earlier on in the video, I said that not all decimals are fractions. You probably want me to explain. Well, watch my next video for that. Thank you for listening.